I'm Angelos Kokkinos. I work for Babcock Power, non-related to Babcock and Wilcox. I have over 37 years of boiler design and combustion experience. So this is basically heat rate 101, actually heat rate 001. I'm a chemical engineer by trade, and as such, I had help from our boiler design group in coming and showing you some of the numbers that I'm showing you, since I skipped most of the thermodynamic classes that I took in college. I had excellent attendance, however, at the distillation course. So let me just start out first with a typical coal-fired power plant. And so you can get an idea what's going on, what gets into in measuring and trying to figure out what its efficiency is. You basically have pulverized coal, which is combusted inside the furnace. So you get water, which you heat up, you make steam, you superheat the steam, you take it into a turbine, and then the steam expands into the turbine, so it rotates, creates kinetic energy. It goes back, and it gets injected into what they call the reheater, which reheats it up, dries it up basically, sends it into the turbine to have more energy taken out of it, and then from there it's condensed and the cycle starts all over again. I'm gonna skip this because I wanna show you a typical power plant cycle. It has 4 major components, a power plant. The boiler, which generates the steam, the turbine, which uses the energy from the steam to turn the generator. It has the condenser, which takes the spent steam, which is now very low pressure and low temperature, makes it into water. And it has a feed pump, and that feed pump raises its pressure, the pressure of water, back up again to such that the cycle can start again. So it's the same schematic that I showed you as before. Just to give you an idea of the numbers that we're talking about, steam temperatures and pressures. Steam temperature on a typical plant is about 1,000 degrees Fahrenheit. Its pressure is about 2,500 degrees pounds per square inch. So these are the pressures and temperatures that you're talking about. So how does the process work? You have several steps in this diagram, and it's called the Rankine cycle, where the first step is to increase the pressure of the water to the operating pressure, the 2,500 psi. So you get some increase in temperature, and then you get that increase in temperature by running it through what is called the economizer inside the boiler. Then beyond that, from this point on, which is step 2, to this step, you take that water and you boil it, then you superheat it, take all the steam, all the water out of the boiling water, and then you send it into the turbine, which happens in between steps 3 and 4. The steam expands into the turbine, and then you take it, send it back into the boiler, you reheat it, send it into the turbine again, and then it expands, and then you condense it out, and you start the cycle all over again. Now there's another typical power plant that you probably have heard of, and that is the combustion turbine combined cycle process. And that's, again, another one that is quite popular because it has better efficiencies than the cycle that I just showed you. And basically what you do there, what you have is you have a combustion turbine, which is nothing more than a jet engine, where you take air, you compress it, you put it into a combustion chamber with fuel, and when it combusts, it runs through a gas turbine. The turbine obviously turns a generator. You take the exhaust gas from the combustion turbine and you run it through a heat recovery steam generator, which is nothing more than the boiler that I just described to you earlier, except that it doesn't have a flame in it. All it has is a hot gas. And then obviously the exhaust, you send it out the stack, but the heat recovery steam generator makes steam, which goes into a steam turbine and a generator, just like the coal unit has, and then it goes to a condenser, and then back up again, gets recycled, and the cycle starts all over again. Now, in the combustion turbine combined cycle, why they call it a combined cycle is because you take two cycles, two thermodynamic cycles, and you combine them. The first one is the gas turbine cycle, or as they call it, the Brayton cycle, which is the darker part, and you combine it with the Rankine cycle, which is the pulverized coal, as I would call it, boiler cycle, which is the lighter gray. And when you add up the shaded areas between these two, that's what you get. That's why you get the better efficiency. And typically, the efficiency is as high as 50 to sometimes 60% better than a Rankine cycle. Now, what is heat rate? And I gotta go back a little bit. Why are we talking about heat rate? And as I'm sure all of you are aware, on June 2nd, the EPA proposed regulations for the existing power plants to basically control carbon greenhouse gases. And the EPA suggested CO2 emissions for each state on the basis of pounds per megawatt hour. And the EPA also suggested that there were 4 possible ways of achieving those numbers. The first of which was a 6% improvement in the heat rate or on the efficiency of a pulverized or a coal-fired power plant. Okay. Now, that is basically the heat rate. And the heat rate, what it is it measures the combined performance of the turbine cycle, the boiler cycle, and all the power auxiliaries that are associated with generating electricity. And they measure that against how much fuel is consumed. So it's a very simple formula, which is how much fuel you consume times its heating value, and you divide that by how many megawatts you send out the line to the consumer. Very simple. So the plant efficiency rate means that as the fuel heat input increases for the same megawatts, it means your efficiency is going down. So, because you're consuming more fuel. So, when you look at improving heat rate on an existing plant, what you got to do is you got to look at what are the losses that an existing plant has that I can control, that I can personally control as an operator. I have a design of a boiler, I have a design of a turbine, and all the ancillary equipment that goes with it, that it's a given. So what can I do now to control those losses? And we break them down into several areas. And specifically, we look at what is impacted by the plant operation. And one of the things that you look at is the operating load. And I have some slides that I will show you the impact of some of those conditions. The steam conditions, very simple. The higher the pressure, the higher the temperature of the steam, the better efficiency you'll get. The more energy the steam has for the same amount of heat energy that you're putting in. The condenser pressure. And the reason why the condenser comes into play is because, as I will show you further down, 60% of the energy that you put in gets lost in the condenser. It's a significant amount. The water temperature that you put into what they call feed water temperature, which is the water temperature entering the boiler. The colder the water, the more energy you have to put in. Steam antiperspiration flows. This is steam that you use. It's water that you use to maintain the proper steam temperatures. That's a loss. And of course, auxiliary steam and power consumption, very important. You have a lot of pumps, you have a lot of fans, you have a lot of electric motors in the power plant that consume power. And last but not least, the boiler exit gas temperature and operating oxygen. And I will go through in a little bit more detail on each one of those. So let's look at a theoretical plant, coal-fired plant, and look at these controllable losses and their impact on heat rate. And we are assuming here an 10,000 BTUs per kilowatt hour heat rate. That means to make 1 kilowatt hour, we consume 10,000 BTUs, which is approximately 1 pound of coal, bituminous coal, typical heating value of 10,000 BTUs per pound. So the main steam temperature, that's the first temperature, the superheated steam that I told you that goes into the what is called the high pressure side of the turbine, or the high pressure turbine. If this main steam temperature is 10 degrees lower than what it was designed, you would lose approximately 0.17% of that 10,000 megawatt. So BTUs. The reheat temperature, that's the reheat steam that goes into the lower pressure steam turbine, 0.16%. If the main steam pressure is less than 1%, is lower than design by 1%, meaning about 25 pounds per square inch, you only lose 0.06%. Condenser pressure, and that's the big one. If the pressure in the condenser is half an inch of mercury higher than what it was designed, you would lose 0.6%. Feed water temperature being 10 degrees less, 0.27. Superheated flow, spray flow, not that big. Reheat spray flow, very important, 0.4%. Auxiliary steam flow, this is steam flow that you use to run pumps, to run the soot blowers, to clean the boiler wall so you can get good heat transfer, because coal has ash and it slags up and it prevents heat transfer. That's about 0.35. Excess oxygen, 1% lower which is about 5% in excess air, is 0.2. Again, why is oxygen, why air is so important? Remember, fuel needs air to burn. Fuel needs oxygen to burn. So for every pound of pulverized coal that you inject, you need theoretically about 8 pounds of air. So there's a lot of losses that happen with that air after it goes through and it does its job and burns the fuel. As it goes out the stack, you lose some energy out of it, and I'll show you the numbers on that. Auxiliary power, 1 megawatt is 0.2%, that's all your motors. And the exit temperature coming out of your air heater, you heard about the air heater and the precipitator, that's 10 degrees are worth 0.25%. That means you're sending hot gas out the stack, no different than heating your house and leaving the window open in the wintertime. When you add all these things up, you're about 2.5% losses. So there is room for improvement, and I would as I continue on, you'll see some other areas that have an impact on the heat rate. One of which has a huge impact is the operating load. I don't know how many of you have dug into this new rule, that proposed rule that came up, but they used the Sergeant Lundy report that did an extensive study on impact of different operating parameters. All those numbers that I gave you were at full load, constant load. And this shows the generation of a typical power plant and its impact, 500 megawatt gross, or 450, I believe, or 475 net, as a function of load, meaning how much juice you're sending out the wire. And what you will see here is that up to about 350 megawatts or so, the heat rate is fairly constant. Once you go beyond that point, it takes off. And with the point being that about a quarter of a load, 200 megawatts, you have gone from 10,000 to 11,000, or you have lost 10% on your heat rate. That's amazing. Where does that come into play? And that's very, very important. Where does that come into play? Is at night, or when everybody gets up in the morning and turns on to take their hot showers. Those plants, they have to ramp up, and then they gotta ramp down when there's no demand. And if they're sitting there at partial load, they're losing electricity. And remember, I should have put in it's a very complicated chemical reaction, but it's basically fuel or efficiency is directly related to CO2. When you burn a carbonaceous fuel, when you combust it, is C plus O2 goes to CO2, period. So the more fuel you burn, the more CO2 you're going to. So that is a very key thing that you need to keep in mind. boiler efficiency is directly related. The steam generator's efficiency is directly related on almost at a one-to-one basis to heat rate of the entire power plant. And what is the biggest losses when you do a boiler efficiency calculation is what they call the dry gas loss. So that's just directly related to the amount of air that you use to combust the fuel. So if you put too much air to combust it, you have a lot of what they call excess air, what we call excess air, which basically heat going out the stack. If you have too little air, the fuel doesn't burn very well. You make a lot of carbon, and that's not good because it impacts what it's called combustible losses. Hydrogen and water in the fuel. If you have a fuel that has high nitrogen, for example, methane, natural gas, has more latent heat of vaporization, as they call it. I did take that class. I was in that class. So that natural gas will have higher losses here, but they make it up by having lower excess air requirements. Or if you have a fuel that has a lot of moisture. For example, PRB coal's got 25, 30% moisture versus bituminous coal that has 10% moisture. So there's no, as my mother said, there's no free lunch in this world. Moisture in the air, radiation losses, these are basically losses from the boiler and then unaccounted losses, these are the losses that we original equipment manufacturers take to sort of like we keep those in our pocket, okay? Now, so I'm not going to go through all of these, but just to, again, to reemphasize dry gas loss, and that's impacted by the temperature and the quantity, which is impacted by the excess air, and it's important that people maintain proper boiler exit gas temperatures. Talked about the hydrogen, talked about unburned carbon. Boiler degradation is another problem. As the boilers operate, you will get a lot of junk on their surfaces, and it's sometimes that junk is difficult to get off, and it insulates the surface, and therefore you have to fire more fuel because you control to the steam temperatures and steam pressures that you're supposed to control. Air heaters leak, so you lose some efficiency by basically not heating all the air that you're supposed to be heating. Heating value. Sometimes the coal, even if it's from the same mine, have a tendency to degrade. I talked about the moisture content, hydrogen, slagging and fouling characteristics, again, insulating impact, and last but not least, the sulfur content. If you have a higher sulfur content, what that does is it has a higher acid dew point, so you need to keep the boiler exit temperatures higher so you don't corrode the backpass of the boiler, of the plant. Now, let's just move from the boiler to the turbine. The turbine also has an efficiency. And when you look at it, it's a fairly good machine. It's got the high pressure side, runs between 78 and 84% efficiency, and the intermediate side runs into in the upper 80s, low 90s. Similar calculation, turbine heat rate, energy input over the power output, and the net heat plant rate is really just the turbine rate divided by the boiler efficiency. So what happens, what items impact the turbine efficiency beyond the fact that I talked about the steam temperatures and pressures? One is deposition. There are in the water has minerals, and the power plants go into extensive efforts to demineralize the water, but they still get some small amounts of minerals, and those deposit on the blades, and the blades throw the aerodynamics of the blades of the turbine off, and that basically has some friction loss. Erosion. Erosion comes up if they going up and down on load and they get some condensation of the steam. You get some erosion on the blade. There's mechanical damage, and there's also internal leakage between the different stages. The other thing that impacts it is not so much the variable pressure operation that actually helps it, but it's actually operating at constant pressure as you move up and down the turbine load. So that has an impact. And last but not least is partial arc admission, which means that if you inject the steam, especially at partial loads, at one part of the injection rather than having a uniform injection of the steam going into the turbine. Condenser. As I mentioned earlier, 60% of the energy from the steam generated is transferred to the condenser, so it is lost. Okay. But basically, the purpose of the condenser is after the steam has gone through all the different stages of the turbine, is to convert it back into water so you can pump it back up into the boiler. So what you need to do is you need to reduce the pressure that the condenser has in the whole circuitry of the water steam cycle at the turbine outlet below atmosphere, such that you get the maximum energy, kinetic energy, out of the turbine. The less pressure is at the end, the more force you get through the turbine. So it is important that what they call the back pressure of the condenser is kept at its minimum. However, you can't just automatically go in and say, okay, I'm going to put in minimum pressure. I'm going to design the condenser at minimum pressure. I'm going to replace it with something that gives minimum pressure, because it operates in sync with the turbine outlet. So the turbine outlet, it changes. If you make one change to the condenser to reduce its pressure, it changes the outlet aerodynamics of the turbine, and it could have the opposite effect of what you're trying to do. So if one looks at how you can do that, you have to do that in conjunction with the turbine design. So what are the impacted? What is the impact? Cooling water inlet temperature impacts the performance of the condenser. On a hot day, usually they have cooling water. Some of the condensers get the cooling water from a lake or from a stream, a water stream. Others use cooling towers. If it's a hot day, you got hot water coming in. Therefore, the condenser is not as efficient as it should be picking up. The heat load, how much heat is in there. Circulating water flow is another one. If you have fouling inside the tubes, or if you have some tubes that have gone bad and you plug them up so you don't have any leaks or anything like that, that impacts it. The other equipment that impacts in the power plant heat rate is feed water heaters. Feed water heaters uh, basically take the water that comes out of the condenser and they heat it up using steam that is extracted from the turbine to heat it up to a high temperature such that it can be reintroduced back into the boiler. They're usually in series, and there's usually, depending on the boiler size, anywhere from 2 to like 6, 7 of them. And if you have some of them out of service, what that means is that you're not getting the temperature that the boiler requires to operate at its optimum efficiency uh, at that level that is required. So therefore, you're losing energy. The other thing that happens is they are mechanical devices. They have a tendency to leak, so they would plug them up, and that would means that you're losing some heating surface. Um, and the last one is the cooling tower. Some power plants have cooling towers. You all have seen them in the news. They are the big parabolic. Some of them are parabolic trough design, and they are always mistakenly identified as nuclear power plants and nuclear reactors, or are mistakenly identified as being pollution sources where all you get is water vapor. But anyway, those are also impact because if they don't operate properly, they don't provide the right temperature, the cooling temperature that the condenser requires. And there's three things that can impact it. One is the water distribution, how the water flows through the cooling tower. The fill, these cooling towers have fill or packing to allow for good contact between the air and the water that they're trying to cool. And last but not least is the airflow. For example, a parabolic cooling tower won't have the airflow problem because there's nothing in there. It's a natural draft flow of the air. Whereas a cooling tower that has a fan that it's a forced air cooling tower has fans, so there's possibility that you don't get good airflow distribution. And I believe, so in summary, maintaining the current equipment to the as designed condition is not just advisable, but strongly advisable. Achieving as designed efficiency on a daily basis is difficult due to, as I mentioned, fuel quality variations, equipment variations, weather conditions, and scheduled equipment maintenance. Load dispatch impacts heat rate, ramp rate, and if the unit is peaking as opposed to a base loaded unit. Having said all that, fuel costs are being a major portion of the operating cost of the power plant. And we're talking about the numbers that I have seen are in the order of 60 to 70, 75% of the operating cost of a plant. Have forced operators, including utilities that are state regulated, to attempt or operate at optimum heat rate. I'm not saying that they're operating at the original design, but that's how, as I know, people in management get that is one of their evaluation criteria, is what is the heat rate of your plant that you're managing. So the last bullet, probably I should duck or something. Can you turn off the, oh, it's too late. The 6% heat rate improvement, I think it's going to be difficult to achieve without doing some equipment modifications. And with that, I will run out before any question. No, seriously, you can ask me questions. But that's my, this is my personal opinion. It's not Babcock Power's opinion, it's not, but this is my personal opinion. So, any questions? Yes, sir. With the question was, there's combined cycle units that use water injection to control NOx emissions. I don't have specific numbers on the impact and the efficiency, but having done quite a lot of work in my younger days on NOx controls, I'm sure the amount of moisture that is added it's very small compared to, so it would be minimal impact on the efficiency. Yes, sir. The question is, which I refuse to answer. The question, seriously, the question was, if it's difficult to achieve the 6%, what is my personal opinion on what could be achieved? I think that probably at full load, and I have to qualify that, at full load, base loaded unit, maybe 2%.
Hey, Angelos, as an old boiler guy myself, it depends a lot on the kind of plant you have. So if you got a brand new plant, there's probably little as any
That's right.
improvement that you're going to make. If you got an old plant that maybe hasn't been maintained as well and might not have been maintained as well for a lot of reasons, like we don't operate it very often, so
Right.
it's hard to justify putting money into those plants. If for some reason they now have the opportunity to operate at a higher capacity factor, they may decide to pump money into those plants, and they could, in fact, they could make 6%, depending on
Right.
how old the plant is,
That's right.
how long it's been running, and what condition it's in. But there's also a lot of things coming down the pipe, like cooling, right? People are trying to get people to quit using river water and lake water to cool and want to go to dry cooling. Has the opposite impact. It's going to.
That's right. By the way, dry cooling, it's an efficiency loss. Big time. Big time. So that, but I think he is correct. He is correct that it's a new plant is going to be a lot easier. You can't get much out of it. Yes, ma'am. I think your question is, are you talking about the change in fuels that is happening between coal to gas, or the retirements? What impact that would have on the? We have not studied it. I'm in the group that actually does that work for the company, but we haven't started looking at that yet. We have been concentrating more on the natural gas conversions and the retirements versus looking, because this just came in. And by the way, I don't want to be a state regulator. And the reason for it is because in those four conditions, there's a couple of other things that would make me stay awake at night, and that is the impact of the 70%, what I would call capacity factor on combined cycle units, which changes the overall dispatch situation for energy of the power plants within the state. And the other one being 1.5% in basically efficiency improvements statewide. So it's a very difficult model to try and analyze. I guess I'm an engineer, so I got a problem with modeling to begin with, unless it has something to do with burner design or fuel or boiler design. So I don't know, very difficult. Yes, sir.
That chart that you had on the efficiency based on the size of megawatt units, is that based on the unit size itself, or was that based on what the problem was?
No, but we just used a 500 megawatt unit. That's how we started out with. Yeah. So I've been given the hook. So with that was the last question.